Hi. Okay, so if you were absent from class today, whoops, we're going to learn about diprotic acids. Okay, and these are the notes that you missed. So first of all, you should have a copy of this KAKB sheet. If you don't have one, it's on Schoology. It's in the Chapter 14 folder. Okay, but you might want to pull that out. You'll need it for today's lesson. All right, so this in your Chapter 14 binder packet is page 7 to 9. And like kind of looking at the notes in general, going all the way back to page 5, we've learned a lot of different things. We've learned how to determine the pH of just about everything. Weak acid, I'm going to go back a little further. Strong acids, strong bases. This is page 5. Weak acids, weak bases. Okay, and then we learn all kinds of different things we can do with the general concept. But today we're going to do diprotic acids. Okay, so first of all, some examples of diprotic acids. That just means you have two acidic hydrogens out front. So sulfuric acid is a great example. Come up with a couple other examples. I'm looking at that Ka-Kb sheet that I just flashed in front of you a minute ago. And let's see, how about carbonic acid? That's a good example. That's what's found in any carbonated beverage. Another one, oxalic acid. Okay, that's like a really hardcore, actually like bathtub cleaner sort of thing. So H2C2O4. Let's see if there's any other good ones that I like. Ascorbic acid. That's actually code name for vitamin C. And this one's kind of interesting because there's lots of hydrogen. Okay, there's the 2 here and the 6 here. The 2 here, these are the ones that have, make it an acid, have acid properties. These 6 right here are just sort of along for the ride. Okay, so what about polyprotic? That means 3 or more H pluses. So citric acid is a great example. Another example on the Ka-Kb sheet is phosphoric acid. All right, and I guess citric acid is another great example. Found in orange juice, things like that. Actually, Sour Patch Kids are like concentrated citric acid. Very yummy. All right, so we got some examples. Okay, so what makes diprotic and polyprotic acids unique? So they dissociate just like any other acid, but the H's come off one at a time. So for carbonic acid, to pull off the first H, okay, you have Ka1, a K value equilibrium constant for just the first H coming off. So if I look at that Ka-Kb sheet, I see that the Ka1 is 4.3 times 10 to the negative 7th. All right, then now we got this guy, and we're going to pull off the second H. Okay, so that's the second dissociation, so we call it Ka2. And the value for that, according to that same Ka-Kb sheet, is 5.6 times 10 to the negative 11. Okay, so what I want you guys to see here, is that if you look at all the examples of diprotic and polyprotic acids, you will see that Ka1 is always larger than Ka2 and larger than Ka3. So the first Ka value is always larger than the second Ka value, and so on. And why is this? Well, it gets harder and harder to remove H plus as you proceed through each ionization. Okay, so we will actually learn more about this later when we sort of look at the structure of acids. But for now, as you go through successive ionizations, it gets harder and harder and harder to remove the H's. Okay. So now, of course, we're going to move on to the math. So if you have a monoprotic acid, you do 1 ice table. If you have a diprotic acid, you're going to set up 2 ice tables. So we're going to do just that. So this is the next page, example 8. We're going to basically determine the pH in every single concentration that we can think of for a 0.2 molar solution of oxalic acid. I'm actually going to skip question A because we'll kind of do that throughout the problem. So we'll start with question B. It says set up a traditional ice table for the first ionization. Okay, and that's nothing new here. Okay, typical ice table. So I'm going to take the formula for oxalic acid, look it up, H2C2O4. Okay, now you have the option of doing the longhand dissociation where you react it with water, or the shorthand one where you just break off the H. So I'm sure you're thinking shorthand sounds good, so we'll do that. Okay, so we broke off our first H plus, and then this guy, HC2O4, it was neutral. You lost an H plus, so it has a minus charge. Be really mindful of those charges. All right, so if this is the acid, HC2O4 minus is the first conjugate base. Okay, so we'll go ahead and set up that ice table. So the molarity started at 0.2 molar, 0, 0 for these guys. So the reaction is going to have to shift forward. It's kind of nice having everything in a 1-to-1-to-1 ratio. Okay, set up a beautiful ice table. So now we can go ahead and look up Ka1. So on that Ka-Kb sheet, if I look it up for oxalic acid, it's 6.5 times 10 to the negative 2. Okay, and then we'll write our expression. So it's going to be H plus HC2O4 minus, and we'll put that over the reactant. All right, looking good. So now 6.5 times 10 to the negative 2. Of course, H plus and HC2O4 minus are both equal to x, so that's x squared over 0.2 minus x. Okay, beautiful. Go ahead and solve. Now, a little easier said than done. So first of all, you might notice a couple things. This right here, as Ka values go, is a fairly large Ka value. Okay, we said that small Ka is 10 to the minus third or smaller. So this weak acid is actually dissociating to a pretty good extent. So what that means is that it would not be appropriate in this case to get rid of this minus x, because this one, 0.2 minus x, it's actually going to make a difference because this reaction is going in a pretty good clip in the forward direction. So as a result, I'm going to get rid of that. We have to use a quadratic formula. Okay. Now, when I say quadratic formula, you can do it old school style or, the graphing method. Okay. Where you just type this into the graphing program, find the y-intercept, and, I don't care what method you use to solve for x. Okay. But it can't be getting rid of that minus x. Okay. Because it would not pass the 5% rule. Now, I'm going to save us some time. And I'll just go ahead and tell you that if you use the graphing method or the quadratic formula, X comes out to 0.086 molar. Okay, so that's all good. Just for future reference, I keep telling you that you're not expected to use the quadratic formula like on a test or on the AP exam. So I think this might be, the first and last time we use quadratic formula or the graphing method to solve for X. So for the most part, all your K values are going to be pretty small, minus third or smaller, so that you can get rid of the minus X. Okay. Hopefully that's clear. As always, if you're unclear on anything, do not hesitate to ask, okay? So X is 0.086. Now, the more important part is, what's the significance of that? Okay, so X equals the H plus concentration. Good. And it also equals the first conjugate. Okay, and the other thing that we can solve is we can go back and we can solve, whoops, that's what I meant to circle, the concentration of the acid. And I'm sorry, I'm writing pretty messy here as it turns out. So I'm going to take that 0.20 and I'm going to minus x. And it actually goes down a pretty fair amount, down to 0.11 molar. So about 40% dissociation or something like that. All right, so that is the first ice table. Absolutely beautiful. Okay, nothing out of the ordinary. Okay, so now we're going to move on, and it's a diprotic acid. So now we're going to have to deal with the second dissociation and a second ice table. So that's what this is describing, but I'm going to put it on the next page. So let's see. What would be the most beautiful dissociation reaction for the second dissociation? So I'm going to take that HC2O4 minus, and now I'm going to get rid of that H. Okay, and just for the fun of it, I'm going to use the longhand notation just because I want you to be really flexible with either way. Okay, so that H is going to look at that. I showed the direction wrong. The H is going to transfer this way, and we're going to be left with C2O42 minus. Right, it had a -1 charge, but we lost an H plus, so it got one step more negative. And then, of course, H3O plus, okay, from the water accepting the H. Okay, so now we're going to do our ice table. All right, now here's the fun part. What values from this ice table and from what we solved here are going to transfer down to the next ice table? So one ice table leads to the next. So right now, that 0.086 can become really important because that is my starting concentration for this first conjugate. Okay, and then what's really interesting is we also have some H3O plus or H plus, right? Remember, they're the same thing present. So that number is also going to carry down to this spot as well. Okay, and this guy is 0 because we didn't calculate any of that from the first ice table. So that right there is what makes determining the pH for diprotic acids interesting. Okay, because one ice table leads to the next, and this value right here comes down to the next ice table. Okay, so you have 0.086 molar HC2O4 minus present and 0.086 molar H0 plus or H plus present as well. Okay, so now it's a normal ice table. So still going to shift in the forward direction because we have to generate some of the second conjugate. Okay, so it looks something like this. All right, rocking and rolling here. So now you guys can go ahead and set up the Ka2 expression. So I'm going to look up Ka2 on that KAKB sheet. Oxalic acid, 6.1 times 10 to the negative fifth. Okay, and it's still products over reactants, so it's X times 0.086 plus X on top, my two products, 0.086 minus X on the bottom. Okay, now here's where some really interesting things happen. So let's talk about this K value. 10 to the negative fifth, that is definitely a very small K value. Okay, so what that means is that this reaction is not going to proceed very far in the forward direction. Okay, and I'm going to add to that, what about the presence of the H3O plus or H plus? The fact that this isn't zero and we already have some H plus sitting there, if you think about Le Chatelier's principle, if this a value is high, that's even going to shift the reaction less in the forward direction. Okay, so for two reasons, because of the small Ka value and because there's H plus or H3O plus already present, this dissociation is really, really not going to shift very far in the forward direction. Okay, so that being said, what is 0.086 minus a really, 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 really small number? Okay, well, I will tell you that it will not make a difference. Okay, it will be 0.086. And folks, if you can do that on the bottom, you can definitely do that on the top too, because 0.086 plus a really, 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 really small number is going to be 0.086. So you absolutely can do that simplification. But there's even more, because basically what you're looking at now, if I clean this up a little bit, okay, this kind of went away, this went away. So basically, it's 0.086x over 0.086. Well, heck, you can get rid of this too. So long story short, when it's all said and done, when you solve the second ice table for x, x ends up equaling 6.1 times 10 to the negative fifth, or in other words, it equals Ka2. Now, is this a fluke, or is this going to happen every time? And the answer is this will happen every time for diprotic acids. And it just has to do with the fact that you solve for this, and when it came down to the second dissociation by putting that number in both these spots, it's just how it works out. Okay, so in fact, this is more or less a definition. Okay, that the concentration of the second conjugate base, and you know what I mean by that, right? Because the first conjugate base, you got rid of the first H. The second conjugate base is when you get rid of the second H, that concentration will always be equal to Ka2. So what's really nice about it is, like on a multiple choice test or something without a calculator, I can give you this really complicated problem, but ask, oh, what's the concentration of the second conjugate base? Boom, the answer is Ka2. You don't even have to do any math. You don't have to think about it. It's a definition, okay? So put some stars by that, whatever you need to do, because you definitely want to remember that. All right, so what about the rest of the ice table? Well, you know what? You can go back and you can think about the HC2O42 minus, okay? And it was 0.086 from the first ice table, and it went down by just a little bit. But guess what? This number is not going to make a difference, so it's pretty much still going to be 0.086 molar. Same thing with the H plus. Yeah, you got 0.086 molar H plus from the first dissociation. You got a little bit more from the second dissociation, but I'm going to promise you that with sig figs, it's pretty much 0.086 molar. So take-home message is, did the second ice table really contribute very much? Absolutely not. We got this number from the first ice table. We got this number from the first ice table. The only thing that came out of the second ice table was the fact that the concentration of the second conjugate was equal to Ka2. Whew, so that's a lot of information. So take a minute, make sure you've taken good notes, make sure things are labeled. Okay, and we're going to summarize that here below. Here's some really nice, pretty work. Okay, I kind of cleaned it up a little bit, if that helps you at all. Okay, and then to summarize. So point number one, the C2O42 minus, the second conjugate base, was equal to Ka2. And in general, A2 minus, that's like code for the second conjugate base, because you got rid of the first H, and then you got rid of the second H, so that's why it's A2 minus. Will always be equal to Ka2, okay? No second ice table needed. And then why is that? Since Ka1 was so much greater than Ka2, the second ionization really did not contribute a significant amount of H+. That second dissociation just did not happen very much. So, therefore, you can determine the pH from the H+ from the first ice table, and the same is true for all the other values, okay? So take-home message is, even though it's a diprotic acid, you really only needed the first ice table to do all the calculations. All right. Well, you heard the bell. What perfect timing. But I do have one more thing to say. Your task is now, I want you to do this next example on the next page. Is it page 9, maybe page 10? Anyway, it's determining all the possible concentrations and the pH for a 0.4 molar citric acid solution. Okay. Now, interestingly enough, this is a triprotic or a polyprotic acid. It has 3 acidic hydrogens. So what does that mean? You got to do the first ice table. You got to do the second ice table. You got to do a third ice table. Okay. So that's what makes this one different. But honestly, just like with the diprotic acid, really it's only the first ice table that's significant. Okay. The second dissociation doesn't really offer much, and the third dissociation really doesn't offer much. Okay. So honestly, you really just need to do one ice table. That will allow you to figure this out, this out, this out. And then from the second ice table, you just have to remember that the second conjugate, this guy right here, is equal to Ka2. Now, you might think, oh, but what about the third conjugate? That should be equal to Ka3. Unfortunately, does not work that way. So in order to figure out this one, you have to set up all 3 ice tables. That's the only way you'll see it. There is a pattern to it, so once you do it once, you'll be like fine for life, like you'll understand it. But this is kind of extra credit level. I really don't expect you to necessarily be able to do that unless you're interested, unless you want to. Okay, so you have to be able to do all these parts. So what I would say is sit down, work through this, see how it goes. I think I'm about to flash the answers, but honestly, I would work through it first. Promise me you'll work through it first. Did you promise? Then go ahead and continue on to the answers. Let's see if that's true. Yep. So there you go. So you can look through the first ice table, and from the first ice table, that basically allowed you to figure out the H+, the pH, the original acid concentration, okay, and the conjugate, first conjugate, and then you could figure out the second conjugate, and then you could figure out the third conjugate if you kind of can figure out where those numbers came from. All right. Well, thank you for listening. Please, 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 if you're watching this, that means you were not in class. So if you have questions, that is totally expected. So make sure that you do ask. All right. Thanks for listening. Have a great day.